Okay, thank you. Now, this is not a new technology. We've been working with it in Anger for about 6 years in my group, but this is a new audience, so most people here won't have heard it. So I'm going to rewind and go right back to the beginning of why we invented it. The technology is called SADI, Semantic Automated Discovery and Integration, and it's really just a set of design patterns for web services that natively deal with linked data. So right back at the beginning, we say, what's the problem? Well, the problem is XML schema. Right. So XML schema allows us to describe to a machine the structure of an XML document. Therefore, of course, we can share and aggregate and integrate data. No, we can't, right? So what schema did for us is it gave us, among other things, a way to create automatically memory structures that could hold an XML document, but it doesn't actually go anywhere near solving the integration or aggregation problem. And that's because if we look at these two schemas, one from EMBL, one from GenBank, they actually represent exactly the same data, but their schemas are completely different. And you have to know the meaning of each schema element in order to do the integration. And to do that, we resort to schema mapping. So we say, well, this piece of text, which is attribute name in EMBL, is going to be this piece of text, which is attribute GB qualifier name in GenBank. And similarly, with this piece of free text is a value, and this is the qualified value in GenBank. So obviously, all we have to do then is automate the process of schema mapping, and then we achieve interoperability. Well, that's not going to happen either, right? There's been numerous attempts to automate schema mapping, and none of them have actually proven to be reliable in an open web situation. Nevertheless, we have web services, service-oriented architectures, and a whole bunch of other four-letter words that have come out, but the problem is that they're all based on XML schema, right? And that's not going to solve our problem. We're interested in interoperability. And I like this quote from Charles Petrie at Stanford. He said, the phrase practical web services is not intrinsically an oxymoron, but I argue that there are few in existence. Why? Well, I've sort of summarized the idea. It says, because automated schema matching is such a disruptive problem that there's really no point in building modular and reusable services in the first place, because they're too difficult to integrate, so why would we even bother, right? And that moved us into very dark times. Right? We still wanted service-oriented architectures, so rather than modular services, we simply build services that do everything as one function. Right? The services therefore have a much higher complexity, both with respect to the data types that they consume and produce, and the functional description of that service. So perversely, XML schema has actually made the interoperability problem worse. Right? But there's hope, and I'm talking to the right audience here. Linked data and the semantic web movements have provided us with tools that solve many of these problems. For example, RDF replaces XML schema because it says there's really only one data model, and the semantics are no longer implicit in that data model. And that's what we get from OWL. And that's where we come to SADI. So SADI is a semantics-based web services design pattern. We just want to make web services look more like the semantic web and to behave more like the semantic web. It's standards compliant completely. We don't invent anything. It is just a design pattern. And it's a very lightweight design pattern. There's only 2 rules. And the rules were based on our observations of web services functionality, specifically in the bioinformatics space, but we think this is true at least for all of sciences and possibly beyond. Observation number 1 is that web services and bioinformatics create implicit biological relationships between their input and their output. What do I mean by that? Well, here's an example of a web service, which is a very common one. You give me a gene ID, and I'll give you the DNA sequence. Well, the implicit relationship there is that this gene has this DNA sequence. So what we say in our design pattern is make that implicit relationship explicit. The web service should create triples that link the input data to the output data, thus explicitly describing the semantic relationship that it is exposing. Observation number 2, and this is with respect to HTTP GET and HTTP POST. GET actually guarantees that the response relates to the request URI in a very, very predictable way. The semantics of GET in HTTP are very, very well described. POST, on the other hand, does not have very, very clear semantics. What you get out is not necessarily related in any way to what you put in. And that's why web services have a fundamentally different behavior than the semantic web. But we can fix that without breaking any of the rules. So the design pattern number 2 is that the subject URI of the output graph from your service, the triples, is the same as the subject URI of the input graph of your triples. So the output is now explicitly about the input. Right? So now the web services exhibit a very similar behavior to the web itself. Right? Our post to the service behaves very much like a GET. Our interface definitions are very simple. Again, we use OWL. So we say there are 2 OWL classes. One is the input, the other is the output. And our service invocation says, well, I will consume OWL individuals in RDF of class 1, and I will return you OWL individuals in RDF of class 2 of my output class. But remember that the URI of the input and the URI of the output class are the same. Right? So I'll slow down now and just walk through this. So service description on the top, our input OWL class is a named individual defined as things that have a name property from the FOAF ontology. Our output class is a greeted individual, which is defined as something that has a greeting property from the hello ontology. And then I post some RDF. In this case, it's the graph with rooted at person 1, which is RDF type named individual, and it has a FOAF name of guy incognito. What comes back is a second graph. Again, the root node of that graph is person 1, which is RDF type hello greeted individual, and it has now a greeting property, hello guy incognito. That's all that SADI does. That is the entire spec. Okay. To discover services, because the input and the output are about the same thing, you simply do a diff. Output, diff, input. And that tells you everything that the service does. So I can do a diff and I say, well, that service provides a greeting property to any entity that has a name property. That's what my service does. Every service then becomes an annotation service, but that's actually what most services in bioinformatics do. And then in our registry, we index all of the properties that are consumed or produced by all of the services. So real-world example again, input data, BRCA1, which is of type gene ID. The output data, BRCA1, has DNA sequence, AGCCTTA, and the index in the registry is that the service provides the has DNA sequence property for gene IDs. That's how I discover it. And so when I ask a question, what is the DNA sequence of BRCA1, which is a very common question biologists would ask, we discover that SADI service. And it turns out that these simple little principles are extremely powerful, and I'm going to take you through a couple of use cases right now. So this is a graph data and knowledge explorer from a company called IO Informatics in California called the Knowledge Explorer, and we built a plugin to the Knowledge Explorer. This is what the Knowledge Explorer canvas looks like, and what I've done is pulled in some toxicology data. The 2 toxins are in the bottom left and top right corner of the screen, and all of the genes that are affected by those toxins are mooshed together in the middle. I'll clean that up a little bit. So I've picked the 3 genes that are most highly differentially expressed by these 2 toxins, and I've already asked SADI to go and get me the protein sequences, which are the purple boxes in the center of the screen. Those have been produced using the encodes property, so gene encodes protein. What I'm going to do now is pick one of those protein nodes and say, SADI, tell me what I can do with proteins. And SADI comes back with a menu. And that menu is more or less human readable, right? So has molecular interaction with, is 3D structure for, is encoded by, has motif, has protein sequence, has Go term. Go term, that's what I want. Click, and up come my Go terms. There was no sparkle, there was no nothing. There was just a menu which told me what I could get. We take this many, many, many steps further, and I'm zipping forward in time to SHARE, which is the Semantic Health and Research Environment. This is a piece of magic software, which is a Sparkle engine, plus registry lookup on SADI, plus service invocation, plus workflow orchestration, plus DL reasoning, all in one little box. And what it does is it answers arbitrary Sparkle queries by finding and executing semantic web services encoded in SADI. So for example, this is a very simple example. Select the allele, the image in the description where the locus is deficiens. It has variant allele. The allele is visualized by some image, and the image has some description. There's no from clause because there's no Sparkle endpoint. All of this is going to be resolved by Semantic Web Services. So the machine has to figure out where those services are and how to access them. And we put that into share, which is just a big blank box like this, and we click submit, and it comes back with an answer. And of course, because it's Semantic Web, all of these answers are live hyperlinks directly into their source databases. And you say, well, okay, but we could have done that much more efficiently with a federated Sparkle query. That's true, okay? But we did answer this without a Sparkle endpoint, and the point is that that data didn't have to exist, right? Look at this example. Show me the latest blood urea nitrogen and creatinine levels of patients who are rejecting their liver transplants. So the question is, select the patient and the urea nitrogen, the creatinine from, in this case I actually do have an RDF table of patient data, and the patient is of type likely rejecter, and they have latest creatinine and latest urea nitrogen. This clause here, patient is of type likely rejecter, I've defined that as a patient who has creatinine levels that are increasing over time. Right? The problem is that our triple store contains blood chemistry measurements at time points, but nothing else. Right? It does not have a likely rejecter property, it does not have a table, it does not have anything. That information doesn't exist in the database. So what share does is it decomposes the OWL-DL definition of a likely rejecter, and it determines by reasoning that it needs to do a linear regression analysis over creatinine blood chemistry measurements, because one of the properties in that OWL definition is linear regression slope. So it starts to map things onto web services, figures out how to interact with that service, packages up the data, and sends it. It figures out how and where to do that analysis all by itself. It orchestrates the workflow to do it by itself, and it does it. And you'll see here, this is a screenshot of share actually resolving that query, and it's found the service linear regression, and it's calling it. And voila, it comes back with an answer. So it formulated a workflow to generate the data de novo, because the data that was required to answer the query didn't exist. And that's all I want to tell you for now, but please go and look at the details of this talk at the following URL, and it's an open source initiative. Please contact us if you're interested in seeing more about how we do this. markw@illumine.com. Thanks.
Thank you. Any questions?
I really like the idea behind SADI and what it's capable of doing. I think that's very cool. So forgive me if this question is not directly about that, but I'm not sure that I understand how you solved the original problem that you told us about, where you needed to map two different formats to an understanding of what they both meant. Because in SADI, I don't see that there's two different formats. You seem to only have one format for each thing that you're actually producing.
It puts the problem in a different place, right? So if there are several ways. So first of all, the reasoner can figure it out. The two data structures do not have to be identical, and this is one of the nice things about using semantic data, is that so long as I know that my data is semantically equivalent to the data defined by the interface, I can just pass it verbatim, because the service will reach in and take out the data that it needs. So if I have a more complicated object, that's fine. Just throw the whole thing at the service, and the service will take only what it needs. So there's no schema. Right? It's only semantics. So in principle, let me give you an example. Let's imagine the worst case scenario is that I don't know what I'm doing, and I just cat my database at a service and just post the entire thing. The service will find the correct data to extract from whatever you just posted it, because it's semantically correct.
Okay, so I feel like you've put the problem, you've moved it to a point where you need to define semantically correct.
Yes.
Okay.
I'm not unhappy with that. I mean, the thing is that the reason we can't map schema is because there is no semantics. And so if you're working in an RDF world, you've already started thinking about semantics anyway. So.
Yeah, I think that's probably the key to it.
Yeah.
I mean, if I call it A and you call it B, we still have to know that semantically they have a common ancestor or something.
Yeah, and there is another aspect, and that is that in my data set, because I can represent the semantics and the data in the same document, I can say in my data set, RDF type A is OWL equivalent to RDF type B, and the service will be fine with that. If I tell it the semantics and how to interpret, it's fine. So there are ways to force a service to interpret correctly.
Okay, we have time for one more question. Are there any? Okay, thank you very much.
Thank you.